The first thing to do is to install the library from the PAE repository. In case you already have another version installed in your computer, we always suggest updating it. Once in our code, we import the verification module, from which, after creating an instance, will then allow us to use all the functionality of the library. We then connect a RealSense camera, and by calling the capture frame function of our library, we can start to record our files. We pass as parameters the frames, the title of our file we want to store, and the quality settings between 0 and 4. We then set up the environment we want to measure and then click play. As we may see, the files are being now recorded. As we see, the file has been saved. In order to show it, we call the function showFiles. We pass as parameter the frame from which we want to obtain information and the file's name. This function will return 3 datasets. We'll be most interested in the depth frame values, as they will be very important in order to create our point cloud, which is made by calling our function pointCloud. We will also have to indicate the name of the given folder we want to create. This function returns 3 parameters that have been used in order to generalize the point cloud computation for any given dataset. We can see that a folder has been created, with the point cloud file and a constructor image. Now we call the segmentation function with the point cloud file we just created and the point cloud parameters. Our segmentation algorithm implements a double plane detection. Firstly, the wall will be detected. We may also see the plane equation and its orientation. This will be quite useful when deciding which type of point cloud we are facing. We will later see why. In this case, the second detection gives us the desired object. We can also see the distance of the background plane and the plane equation for this new object. We finally observe all the elements that have not been detected, but also the distance to the desired object and its variance in the camera axis. We are storing the variance and the orientation in order to distinguish between a tilted point cloud and an horizontal one. Let's see what happens when we are in the first case. This point cloud is tilted in relation to the camera axis, not only the background plane, but also the desired element and the floor. This causes the double plane segmentation to work different. We see the background is detected as in the other case, with a 10-degree orientation. But we see that the floor is detected in the second stage instead of the previous object. We still have the distance to the background plane, but in this case, in the not segmented elements, we can find our desired object. In this case, the variance is very high. Making a ponderation between the orientation and the second detection variance, we can estimate if the third segmentation is needed. A DB-scan clustering algorithm has been implemented. In order to select the desired object from all the clusters, we take into account the quantity of points and its variance. We can see as the desired object is the cluster that satisfies mostly the ponderation between variance and points. Finally, we can see the distance to the object. In order to compare our obtained distance with the real one, we import a txt file indicating the environment's real distances. By calling our function and indicating our position and the orientation of the camera, we observe the environment plot with the camera and its field of view. In this case, our camera is observing directly the column and the background plane. We also have the distance function computation that allows us to divide components using derivatives. This enables the real distance calculation. We observe how it returns the distance to the background and to the column. There are some cases when our camera doesn't observe columns. We need our segmentation algorithm to know this, so we return a parameter with a 1 or a 0. In this case, the function only returns the distance to the 2 walls.